Hello student, now we are going to discuss carbon dioxide transport. So, carbon dioxide transport, first you look at this schematic diagram, right? So, at the level of alveoli, what is the partial pressure of carbon dioxide? PCO2 at the level of alveoli is 40, that is the 40 millimeter of mercury. Then you look at this circle, this is nothing but the schematic diagram of your circulation. This is the arterial side and the opposite side is the venous side, right? This is the venous side. So now my question is, what is the partial pressure of carbon dioxide at the level of arterial blood? So the PCO2, okay, I can put a small a, that is the arterial blood, is 40 millimeter of mercury. With this partial pressure, if I ask you what is the content of carbon dioxide in the arterial blood, CCO2, content of carbon dioxide, then your answer is 48 ml of carbon dioxide is present per deciliter of blood. So please try to understand the difference between these two things. The amount of carbon dioxide in the arterial blood is 48 ml of carbon dioxide is present in 100 ml of blood, that is 1 deciliter of blood. What is the partial pressure of that carbon dioxide is 40 millimeter of mercury. Same way, if you look at the venous side, then venous side partial pressure of carbon dioxide PVCO2 is 46 millimeter of mercury, right? 46 millimeter of mercury according to Ginam, and Guyton is saying 45, right? Whatever. And content of the carbon dioxide is 52 ml per deciliter of blood. So again, if you look at the content, it is 52 per 100 ml of blood, and partial pressure is 46 millimeter of mercury. So I can understand that there is a difference between venous blood and arterial blood carbon dioxide, and that difference is how much? 4 ml per deciliter of blood. So obvious thing is that where from this carbon dioxide is coming, I can easily understand that this is produced at the level of tissue. So tissue is producing carbon dioxide, and how much carbon dioxide is added up in the venous blood? 4 ml carbon dioxide is added up in the venous blood. How much amount of venous blood? In 100 ml of venous blood. So extra 4 ml of carbon dioxide is present in the venous blood. In carbon dioxide transport chapter, we are going to discuss that how this 4 ml extra carbon dioxide is transported by the venous blood. Getting my point? This is the intro. So now we look at the carbon dioxide transport occurs in various format. Carbon dioxide transport, okay? Most of the MCQs are asked from this different format only. So it can be transported in the plasma also, or it can be transported through RBC also, okay? It can be transported through RBC also. If I look at the plasma, what are the different format of carbon dioxide transport? So number one is the dissolved carbon dioxide, okay? So that is DCO2. I am writing simply like this. So there is same like that of the dissolved oxygen, right? Then second is the carb amino compound. Carb amino compound. So what is that? Carb amino compound means carbon dioxide is attached with amine group, NH2 group. So in plasma, we know that there are plasma protein. So whenever the carbon dioxide is attached with the plasma protein, then amine group of plasma protein, then that is known as the carb amino compound, right? So I'm writing here CO2 attached with NH2 group of plasma protein. And then carbon dioxide also forms bicarbonate after reacting with water. So the third form is the bicarbonate formation, right? So at the level of plasma, there are three format of carbon dioxide. Same way, if you look at the level of RBC also, RBC means it will also have some water, okay? So there will be dissolved carbon dioxide also, okay? There will be dissolved carbon dioxide, right? There will be carb amino compound here also, carb amino compound. So how the carb amino compound will be formed inside the RBC? Inside the RBC, hemoglobin is there. So whenever the carbon dioxide is attached with the NH2 group of the hemoglobin, that is the carb amino compound inside RBC. And inside the RBC, obviously, the bicarbonate formation is also going to happen. So now if you look at the carbon dioxide transport, whether it is plasma or in the RBC, there are three main formats. Okay, there is bicarbonate formation, carb amino compound formation, and dissolved format. So MCQ that has been asked already, that which format is the maximum? Carbon dioxide is mainly transported by which format? Now look at the percentage. You may not remember all this detailed percentage, but dissolved format, whether it is RBC or whether it is plasma, this is always 5%. So total 10% is the dissolved format. Then carb amino compound, if you look at the plasma, then it is only 1% of the total carbon dioxide transport, and inside the RBC, this is 21% of the total carbon dioxide transport. So question is, why the carb amino compound is more at the level of RBC rather than the plasma? You look at the percentage of plasma protein which is forming the carb amino compound in plasma, and if you look at the percentage of hemoglobin which is forming the carb amino compound in RBC. So what is the plasma protein concentration? The average plasma protein concentration is 8 gram percentage. We all know this, right? But if you look at the hemoglobin concentration inside the RBC, hemoglobin concentration inside the RBC, hemoglobin per volume of RBC, that is the MCHC, that is 33%. So obviously the hemoglobin which is forming carb amino compound, that concentration is higher than that of the plasma protein concentration, and that's why the carb amino compound is more in RBC. Now if you look at the bicarbonate formation percentage, okay, it is 5% at the level of plasma, and it is 63% at the level of RBC. So now I can understand that bicarbonate is a major format, 63% at the level of RBC and 5% at the level of plasma, means almost 68 to 70% of carbon dioxide is transported in the bicarbonate format. If you look at Guyton's textbook of physiology, Guyton is saying for bicarbonate formation, as bicarbonate formation, carbon dioxide transport is approximately 70%. Another 23% is in the form of carb amino compound formation, and 7% is in the form of dissolved carbon dioxide, right? So this is according to Guyton. So the percentage that I have taken here, this is taken from Barney and Levy. Different books are giving different percentage, but more or less they are similar. Remember, the maximum carbon dioxide transport occurs in the form of bicarbonate formation, and that is also inside the RBC. Now question is, why bicarbonate formation is more inside the RBC? Why this is 63%, whereas it is only 5% in plasma, right? So we all know the reaction. What reaction? Carbon dioxide react with water and it form bicarbonic acid, right? This carbonic acid will be easily divided into H plus ion and HCO3. Right. So this is the reaction by which bicarbonate is formed, whether it is plasma or inside the RBC. And we all know the enzyme which helps in this reaction is carbonic anhydrase enzyme. This carbonic anhydrase enzyme is 5,000 times faster, 5,000 times faster inside RBC, and that's why the major bicarbonate which is formed, that is inside the RBC. Getting my point? The carbonic anhydrase enzyme inside the RBC is 5,000 times faster than that of the plasma. That's why the major form of carbon dioxide transport is the bicarbonate, and that is occurring with the help of RBC. Right. Now we have to understand that how this carbon dioxide transport is occurring at the level of venous blood and at the level of arterial blood, right? So first we are thinking of the arterial blood, venous blood. Okay, so suppose this is your tissues, right? This is the representation of the body tissues. So the tissue is generating more and more carbon dioxide due to metabolism. So this carbon dioxide, by the process of diffusion, it will come out of this tissue, right? Now then this carbon dioxide will enter inside the capillary blood. So this line indicate this is the capillary This is the capillary wall, right? So this carbon dioxide will further penetrate this capillary wall and it will enter inside the plasma portion of the capillary first, right? So what is going to happen when this carbon dioxide is present in the plasma? We have just seen that it is going to form three formats. And what are those three formats? So I am writing here small DCO2, that is the dissolved carbon dioxide, CO2 NH2, that is the carb amino compound, and the third is the bicarbonate. I hope you are understanding what I am writing. So carbon dioxide is forming three formats inside the plasma. But this is not the major one. The major one is that carbon dioxide will enter inside the RBC. So now this is my RBC. Okay. So this is the RBC. Carbon dioxide is going to enter inside this RBC further. Now inside the RBC, whenever the carbon dioxide is entering, again inside the RBC, again it will form the dissolved format, again it will form the carb amino compound, that is it will react with the NH2. It will react with the NH2 group, but I am not writing that. But the main format by which this carbon dioxide will be transported by RBC, you know, that is a bicarbonate. So how that bicarbonate will be formed? So this carbon dioxide is going to react with water inside the RBC. So carbonic anhydrase enzyme is there that will causes generation of the carbonic acid. Now this carbonic acid will be divided into bicarbonate ions and it will be divided into H plus ion. Now whenever carbon dioxide is entering in the RBC, I can understand that there will be production of more and more bicarbonate. So the reaction is going towards the bicarbonate generation. More and more bicarbonate means the concentration of bicarbonate is increasing inside the RBC obviously. So what is the fate of this bicarbonate? This bicarbonate is going to go out of this RBC with the help of an transporter protein or antiporter protein, which will throw this bicarbonate inside the plasma, and in return it will take up chloride molecule from the plasma. So this is an antiporter, chloride bicarbonate antiporter, which is also known as anion exchanger. This is also known as anion exchanger molecule, right? So this anion exchanger, or this is also known as band 3 protein molecule. So what I am saying, so this is an chloride bicarbonate antiporter. This chloride bicarbonate antiporter is also known as anion exchanger type 1, or this is also known as band 3 protein, by which bicarbonate is thrown out of the RBC. This phenomena by which bicarbonate is thrown out of the RBC and chloride is entering inside the RBC, this is known as the chloride shift phenomena or Hamburger effect, CH. Chloride shift phenomena, or this is also known as Hamburger effect, right? So this is very famous chloride shift phenomena or Hamburger effect, right? Now when the chloride is entering inside the RBC, so initially bicarbonate was high, now the chloride is high. So whether it is bicarbonate or chloride, there is presence of extra one molecule or one solute inside the RBC. So what will happen? This is an active osmolytes, active molecule inside the RBC, that is either in the form of bicarbonate or chloride. So due to increased chloride concentration in the RBC, there will be increase in osmotic tension of this RBC, right? If there is increased osmotic tension, all of you know what will happen. There will be osmosis, and due to the process of osmosis, water is going to enter inside the RBC. Which RBC we are talking about? This is the arterial blood RBC or venous blood RBC? Obviously this is venous blood, because we have started from carbon dioxide generation at the level of tissue, and that carbon dioxide is delivered at the level of venous blood. So in venous blood, due to chloride shift or Hamburger effect, water is entering inside the RBC. So what will happen to the volume of individual RBC? Increased. If the volume of the individual RBC is increasing a little bit, theoretically it will be a little bit, what will happen to the total volume of all RBC, that is the packed cell volume or PCV. Remember, the PCV will be high in the venous blood, and that's why we say that PCV of venous blood is higher than arterial blood. How much percentage? 3% higher than venous blood, and that is due to chloride shift phenomena or Hamburger's effect. Because of chloride is entering more in the RBC, the osmotic tension rises, and that takes up water from plasma. Right? Now we have seen what is the fate of this bicarbonate. Now let's discuss what is the fate of this H plus ion, which is also produced by the same reaction. So this H plus ion has to be buffered inside the RBC, right? And what buffer is there inside the RBC? The strong buffer is the hemoglobin buffer. Now we have to think of that the hemoglobin which is present inside this RBC, what kind of hemoglobin that is reaching here? So the blood which is reaching at the level of tissue. Okay, so we have started our discussion from here, the tissue. So the blood which is reaching at the level of tissue, what blood that is? That is arterial blood. Arterial blood means hemoglobin is present in which format? HbO2 format. That is the oxygenated hemoglobin, right? So now this oxygenated hemoglobin, it will try to neutralize this H plus ion. So this H plus ion will react with HbO2, oxygenated hemoglobin. Whenever this reaction is happening, what will happen? It will produce HHB, that is a deoxygenated hemoglobin, and it will release the oxygen. Getting my point? Please look at this reaction. So whenever this H plus ion is reacting with this HbO2, it is producing oxygen and deoxygenated HHB. Okay, now this oxygen, obviously this is a gaseous molecule, right? So gaseous molecule means it will easily penetrate the RBC membrane, then it will reach at the level of plasma, then it will easily penetrate this capillary membrane, and this oxygen will be delivered. Oxygen release will occur at the level of this tissue. So this release of oxygen, whatever is happening here, the phenomena that we have discussed here, that the release of oxygen at the level of tissue is occurring when the carbon dioxide is generated by the level of tissue, right? So in presence of high carbon dioxide at the level of tissue, that carbon dioxide is generating this H plus ion, and that H plus ion is helping release of oxygen from hemoglobin at the level of tissue. So what effect we are talking about? We are talking about Bode's effect. Okay, we are talking about Bode's effect. That's why I told you in the oxygen transport chapter that Bode effect is right shifting of the oxygen hemoglobin dissociation curve due to carbon dioxide or H plus ion excess. So what you are finding out here, we describe the Bode effect like this. We describe the Bode's effect like this, that in presence of high carbon dioxide, okay, in presence of high carbon dioxide or H plus ion, right, increase release of oxygen, increase release of oxygen, increase release of oxygen from hemoglobin. This is nothing but the Bode effect. Or increase release of oxygen from hemoglobin means which kind of shift? Low affinity state of hemoglobin. So what kind of shift? Or you can say the right shifting of the OHDC curve due to which factor? Not due to turbidity, not due to temperature, due to increased carbon dioxide or increased H plus ion, right? So if I ask you that Bode effect is occurring at which places? At the level of lung or at the level of tissue? Easily you can correlate that Bode effect means it is occurring at the level of tissue, right? So I hope all of you are understanding this phenomenon. What is happening? Carbon dioxide entering in the RBC, then it is reacting, H plus ion reacting with the HbO2, and then the oxygen is released, and that oxygen is ultimately going at the level of tissue. Okay, now so this is happening in tissue level, venous blood RBC. Okay, now this venous blood is ultimately going to go at the level of lung, and what will happen at the level of lung? It is going to get oxygenation. So when this RBC is moving at the level of lung, what is going to happen, right? So now it is going towards the lung. Okay, so which form of hemoglobin is going? Look at the form of hemoglobin that is going is HHB. This is reaching at the level of lung inside the RBC. Okay, so I am going to draw the alveoli here. So this is one of the representation alveolus of the lung, right? Okay, and this is the pulmonary capillary. Okay, so huge amount of oxygen is there at the level of alveoli. In presence of huge oxygen, what is going to happen to this RBC? What will happen to this reaction that we have already discussed? Okay, so this oxygen will simply enter inside this plasma, and then this oxygen will further enter inside the RBC. So this is the RBC at the level of lung. So whenever this oxygen is entering at the level of RBC, okay, it is going to react with this HHB, right? It is going to react with the HHB, and whenever it is reacting with HHB, what is going to happen? HbO2 will be produced. Remember, this HbO2, oxygenated hemoglobin, it's a strong acidic molecule in comparison to deoxygenated hemoglobin, right? So in lung, whenever oxygen is entering in the RBC, it is forming oxygenated hemoglobin. Oxygenated hemoglobin or oxyhemoglobin is stronger acid than deoxygenated hemoglobin. What do you mean by acid? Acid means proton donator, means it cannot hold the H plus ion. The H plus ion has to be released from this reaction. Now whenever this H plus ion is released, this H plus ion, now it will going to react with the bicarbonate ion. Now where from this bicarbonate is coming? Bicarbonate already thrown out of the RBC at the level of venous blood. Whenever the RBC is reaching at the level of lung, the reaction will move in the reverse direction, means bicarbonate will again enter inside the RBC, and chloride, which was high inside the RBC, that will be thrown out of the RBC by the same transporter, that is the antiporter anion exchanger, right? This process is known as reverse chloride shift phenomenon. This is known as reverse chloride shift phenomena at the level of lung or at the level of arterial blood, right? So whenever this bicarbonate is entering inside the RBC, this bicarbonate is going to react with the H plus ion. So again this carbonic acid will form, and now the carbonic acid will divide into carbon dioxide, and it will be divided into water. Getting my point? So please note down, this carbonic acid is dividing into carbon dioxide and water. So water will be excess inside the RBC, but look at, the chloride has already been thrown out of the RBC, and this chloride was giving extra osmotic tension to the RBC. Now whenever the chloride is thrown out of the RBC, the osmotic tension of the RBC will be reduced, so this RBC cannot hold this excess water, so this water will go out of this RBC, and again the PCV will return back to normal level. That's why we say that in venous blood RBC size will be a little bit increased, in arterial blood again it will return back to normal because the water is thrown out of the RBC. But what is the fate of this carbon dioxide? Very simple, carbon dioxide, because it's a gaseous molecule, what will happen? This will pass through the RBC membrane, right? Then it will reach at the plasma, then it will pass through this capillary blood, and ultimately this carbon dioxide will be released or will be delivered at the level of alveoli. So now you look at that, in presence of this high oxygen at the level of alveoli, carbon dioxide is released at the level of alveoli. So high oxygen is helping release of carbon dioxide from hemoglobin, from RBC into the lung. This is nothing but your Haldane's effect. This is nothing but your Haldane's effect. Getting my point? So this is known as Haldane effect. In presence of high oxygen tension, carbon dioxide is released from hemoglobin. So if I write down high oxygen tension, high oxygen leads to release of carbon dioxide from hemoglobin, right? Although the effect is looking reverse of the Bode's effect, but it is not exactly the reverse one, because if I ask you Haldane effect means what shift of OHDC curve will happen, oxygen hemoglobin dissociation curve, your answer will be Haldane effect is not related to OHDC curve. Why? What is OHDC curve? OHDC curve is the relationship between oxygen and hemoglobin. And what the Haldane effect is saying? Haldane effect is saying in presence of oxygen, what is the relationship between carbon dioxide and hemoglobin? Whether the carbon dioxide will be released from hemoglobin or the carbon dioxide will not be released from hemoglobin. That effect is Haldane effect. So is it the relationship between oxygen and hemoglobin? Answer is no. Carbon dioxide and hemoglobin relationship is Bode effect. Carbon dioxide release or not, that is Bode effect. That's why the Haldane effect is described with the help of another curve. Okay, Haldane effect is described with the help of another curve, and that curve is known as carbon dioxide dissociation curve. Carbon dioxide dissociation curve. Okay, so far I have not seen any question from the carbon dioxide dissociation curve, but for your future MCQ you have to look at this carbon dioxide dissociation curve also. Okay, so x-axis is the pCO2. Okay, in OHDC curve x-axis was partial pressure of oxygen, but here partial pressure of carbon dioxide. And what is y-axis? Y-axis is the volume of carbon dioxide. Okay, volume of carbon dioxide or amount of carbon dioxide, right? So the curves looks like this. What is the meaning of this curve? Okay, look at, I am putting some point here. So first point is here, that when the partial pressure of carbon dioxide is 46. So what blood I am talking about? Partial pressure of carbon dioxide is 46. So this is the venous blood, right? So I am writing here, this is venous blood. If I drop on perpendicular from this on y-axis, so what will happen to the volume or content of carbon dioxide? I am asking, what is the content of carbon dioxide in venous blood? Tell me, what is the amount contained? That is 52 ml. So here you will get 52 ml carbon dioxide is present, contained amount, right? So in venous blood, this curve is saying that when the partial pressure of carbon dioxide is 46, content of carbon dioxide is 52 ml. What is the partial pressure of oxygen in the venous blood? Partial pressure of oxygen is 40 millimeter of mercury. That is the venous blood partial pressure of oxygen. Now, if I took another point on this curve, and this point is suppose here, if I drop on perpendicular from here, the partial pressure of carbon dioxide is 40. What blood I am talking about? Partial pressure of carbon dioxide 40 means this is the arterial blood you are talking about. If I drop on perpendicular from this point on y-axis, I will find out that this is 50 ml. But is it the actual condition? When the partial pressure of carbon dioxide is 40 ml in the arterial blood, what is the content of carbon dioxide in the arterial blood? That is 48 ml. But here in this curve I am getting 50 ml. So what happening? We are not looking at the oxygen. You are not looking at the oxygen. Look at the oxygen. So whenever you are thinking of the arterial blood, what will happen to the partial pressure of oxygen? That will be 100 millimeter of mercury. Now when the partial pressure of oxygen is 100 millimeter of mercury, look at this carbon dioxide dissociation curve will be shifted in the downward direction like this. So now if the carbon dioxide curve is shifting in a downward direction like this, and on this curve if I take this arterial blood point, because this downward directed curve means this will be shifted in presence of oxygen, which is 100 millimeter of mercury. So whenever it is shifted in the downward direction, now you look at whenever the arterial blood partial pressure of carbon dioxide is 40, it is cutting the curve here at this point. From here, if I drop on perpendicular on the y-axis, then I will find out that this is 848 ml. That means due to the downward shifting of this curve, what is happening? The artery venous carbon dioxide difference is 4 ml, but if there is no shifting of the curve, then artery venous carbon dioxide difference is only 2 ml. Getting my point? That if the curve is not shifting, suppose the curve is not shifting in the downward direction, then what will happen to the artery and venous carbon dioxide difference? Only 2 ml. But because the curve is shifting in the downward direction, so one point I have to take here and another point I have to take here. If I look at the difference between these 2 points, then the difference is 4 ml. So this downward shifting of the carbon dioxide dissociation curve is very, very important for carbon dioxide transport between artery and venous blood. And this downward shifting is also known as Haldane's effect. Okay, this is known as Haldane effect. Getting my point? So downward shifting of the carbon dioxide dissociation curve is known as Haldane effect. What is the advantage of this Haldane effect? Could you tell me? So I can easily understand that because of the downward direction shifting, what is happening? The carbon dioxide difference between this arterial blood and venous blood is doubling. Otherwise, if there is no shifting, how much will be the difference? Only 2 ml. Because the curve is shifting, because of the Haldane effect, what is happening? It is doubling the, doubles the carbon dioxide transport. Okay, getting my point? So please remember that carbon dioxide transport is double by the Haldane effect because the curve is shifting in the downward direction when the partial pressure of oxygen is 100 at the level of arterial blood. That's why venous blood can carry extra 4 ml of carbon dioxide. Without Haldane effect, the venous blood cannot carry extra 4 ml. It can carry only 2 ml of carbon dioxide extra. Right? So this is the carbon dioxide dissociation curve. If I show you the book diagram, okay, so this is the diagram I have taken from book. Okay, so I'll conclude this session with this diagram taken from Guyton. So look at here, this shifting of this A point at the point number B is nothing but Haldane effect. So what is happening? The curve is shifting in the downward direction. Okay, so the above curve, if you look at, this is the curve when the partial pressure of oxygen is 40, that is the venous blood, and the curve which is shifting in the downward direction, this is the arterial blood curve. Because of the shifting, what is the difference of carbon dioxide content between these 2 points? 4 ml. But without shifting, what will be the difference? 2 ml. So this shifting is doubling. Okay, doubles the carbon dioxide transport. That's why it is said that Haldane effect is very, very important for carbon dioxide transport, and Bohr effect is very, very important for oxygen transport or oxygen release. But quantitatively, Haldane effect is more important for carbon dioxide transport than Bohr effect for oxygen transport. So this finishes your carbon dioxide transport.